All right, thank you. So, yes, this is work with my students, Leonid, Peng, and Siyang, supported by the NIH. So this is work about access technology for people who are blind. And if you are blind, there are a bunch of things that are difficult to do, that I kind of listed in no particular order in this acuity chart here. And what I'm really interested in this work is this one here, which is the ability of reading signs posted on walls, what in computer vision is sometimes called scene text, text that can appear everywhere. There are lots of these types of signs in public buildings, like this one here, and they're made for people who are sighted. That would be great if blind people were able to access those. You don't need to change infrastructure, they're right there. So how can a blind person read a piece of text? Well, there are apps on smartphones, and they work really well. Optical character recognition, OCR apps. But there is a problem. And the problem is a problem that I like to call computer vision without sight. So if you're a sighted person, you're taking a picture, you normally look through the viewfinder or the screen or where you're pointing. But if you're blind, you don't know where the text might be. And so in this example here, a blind woman might be looking for an exit sign. The OCR might be able to read it if it was aimed at that, but she doesn't know where that is. So that's kind of like a chicken or egg problem that all camera-based systems for blind people have to deal with. So let me show you an example here of computer vision without sight. And this is based on probably the most used app for text for blind people that's made by Microsoft. It's free, it's called SeeingAI. It has a modality that's called short text, and it does just that. It just reads any text that it finds. So here an example of a blind person using short text. So the OCR worked fine, but if you listen to the text, it's kind of difficult to make some sense of it. Why so? Because this is the part of the image that was seen by the camera. So the camera was not framing the text correctly, but there was no way that this guy could know because it can't see through the viewfinder. Okay, so you need to scan the scene with your camera, but here comes another problem, that SeeingAI, like other OCR systems, do not work while the camera is being moved. So this is a video that I took. So long as I move the camera, the system is not reading anything. As soon as I stop the camera, why is that? Well, because as I move the camera, the image undergoes motion blur. And so here you see that there is some sort of text, but it's blurry. I can't read it, probably you can't, OCR certainly can't. So that's kind of like a double whammy. You need to scan the scene to find the text, but text is not going to be found if you're moving the camera. So to deal with this, we decided to play with something that's called a text spotter. Text spotters are algorithms that are able to detect the presence of text, not to read it, just to figure out that there are some patterns. Like in the case before, we could tell that a blurry thing was text, but we could not read it. They can be very fast, they can be very robust. We developed one of our own, and we decided to apply it for this system. So our text spotter is based on a fully convolutional network. It doesn't run on the smartphone because of memory footprint problem. It could, just we didn't have the resources to make it work on the smartphone. So what we did instead, we streamed images from the smartphone to a server that it ran at, and then the server would send us back information about any text being found. And the whole thing worked at about 2 frames per second. Now, speed is important because if you are scanning something in front of a wall, for example, if the frame rate is too low, you might miss something, right? These are some examples of images whose text has been spotted by the algorithm. It's really good. It works amazingly well also with different types of fonts, different types of background, like the fire thing, the title. It works also when the text is only partially visible. And critically, it can also detect text when it's blurry, which is exactly what we want to do. So how do we use this in a full system? Well, look, this is the Microsoft, the SeeingAI system. There is an image in input. It runs OCR. If it finds something, it reads it all out. Our system has both text spotter and OCR, so it's a little bit more complex. And it does require some action from the user. So it works in this way. The camera looks at images, and as soon as it finds an image with some text, the phone vibrates for a little bit. That prompts the user to stop the camera so that an image of the text, the high resolution that is stable, can be taken. So the text spotter just works as a prompter that there is something there, so stop the camera, We take a good picture, now we should be able to read it. And here is an example of our system we call Spot+OCR in action. So you will see this young man who is scanning that wall, and at some point you notice that he stops in front of a name tag. That's because he felt the vibration on the phone, and after that an image will be taken that will be read. Okay, you also heard that there is some azimuthal information in the interface. On top of this, we also built another system for open spaces. Now, you could just walk around the walls of an open space to try to find text. Blind people tend to get disoriented in open spaces. So we thought about a different mechanism, one in which you just sit in the middle of the space, and you just take very high-resolution pictures sampling the whole space so that you'll be able to capture all text. Now, if you're taking high-resolution pictures, the OCR, we are running the Google OCR API, will take up to several seconds, but that's okay, because you are careful to sample the space correctly, so any text will be there will be read. The system has a mechanism that allows a person to take pictures exactly the right time. So as the user starts taking a picture, the system prompts the user to rotate the camera, then it tells the user when to stop, a picture is taken, prompts the user to move again, and so forth and so on, until the whole space has been covered. And again here, there is no text spotter. We are using we're not going to have moving images. We sample the whole space at high resolution. Okay, so some experiments. Oh, actually, these are the type of images that they're being captured using this guided OCR system by a blind person. You'll see a little yellow arrow there that mimics the prompt to turn the phone around. In practice, there will be an audio prompt. And I'm also showing which parts of the image have been detected. The text was read by the OCR. Notice to the left, that's a lot of circles. That's being read like 0, 0, 0, 0, 0. That's what OCRs do. And so you have to have an option so that you stop this very long list of things being produced. The system reads everything that is found at each picture. Okay, so we ran experiments with 7 blind participants, and they're shown in the next picture here. Now we've done the full 360-degree circle. So these are our participants, and what they did, and I'm going to be very brief here, details are in the paper. They first tested the system in 2 corridors. Actually, we have 2 corridors on 3 floors, a narrow corridor and a wide corridor. They were tasked with going through the corridor back and forth and find all of the text they could find on the left and on the right wall. So they experimented both the SeeingAI system and our Spot+OCR system in different types of corridors. We also had 3 different open spaces, elevator lobbies like 6 by 6 meters, in which they tested in 3 different floors, all 3 different systems, SeeingAI, Spot+OCR with text spotter, and guided OCR, where you just sample the space. One thing that we found out, some people, probably frustrated because SeeingAI was not able to find text, they decided to explore the environment with their hand. Here is an example. So this person found that next to each door there is a name tag. So as soon as we found a door with the white cane, it would start exploring the wall, and then he knew where to aim the camera at. My student thought I was cheating. I told them, that's not cheating. You do your task the best way you can. But of course that complicates the analysis of the results. So here are the results. What I'm showing here first is a test in the corridor. The first plot shows the recall rate. How many pieces of text that were out in the environment, name tags and the like, were correctly read in their entirety. So these are normally short pieces of text, but if only half, say the right half of those were read because just the camera was aiming a little bit too much to the right, that would not count as a success. So we have the 7 participants and highlighted those who actually did some tactile exploration to find text. They only did it with the Microsoft app, with the SeeingAI. Green bars are for our system. The blue bars are for Microsoft SeeingAI. So you'll see that for those who did do tactile exploration, they were very proficient. They had good recall rate. Those who didn't do it, the SeeingAI system basically did not work. Some were not able to find a single sign. And again, because if you're moving the phone at a certain speed, it will not find anything. I'm also showing the speech, the average speed in the corridor in meters per minute. Sorry, this is a mistake, a typo. The use of SeeingAI made for a faster exploration. And that's significantly faster. And this is because our system requires action. You feel a vibration, you need to stop the camera and aim. And there are also some false alarms. So the precision of the Spot+OCR is only 64%. It means that many times you feel the vibration, you stay there, wait for the picture, and the system says, no text found. Why so? Maybe because of a false positive of the text spotter, maybe because you found some text the OCR simply was not able to read because, for example, it was too far. Results with open space system where we try all 3 mechanisms. It turns out that a guided OCR, the one in which you take pictures correctly sampled in angle, gave significantly better results in terms of recall rate, no major differences in terms of time. There was an exit survey. I will just summarize here. Our participants found the guided OCR significantly easier to use than the others. They really liked that vibrational feedback, the fact that at some point the phone vibrates, and you know there is something there. Now, maybe it does not really right away, but you can try other times to explore the space until at some point you might be able to read it. Some desiderata, better feedback, reduction of false alarm, confidence, indication. Would they use it in a public setting with people around? Probably not. They told us that, and it's very common, by the way, with the old camera system. If there are people around you, you don't want to be seen testing things taking a long time. That's pretty typical, I would say. However, if there is nobody around and you're looking for the exit sign, you might want to use a system like this. That's the same for SeeingAI in our system. And I conclude with these observations. So the Spot+OCR system with text spotter is definitely better and finding text than SeeingAI, unless you start exploring the scene with your hand. How many people will do that? Not clear. Not everybody wants to touch all of the walls, not knowing exactly what is there. It does require, however, significant more user interface action by the user, and it takes more time. In general, to find text, distance is very important. If I'm too far from the text, I'm walking in front of a wall, and I'm too far away, there is not enough resolution for the OCR or the text spotter to work. However, if I'm too close to that, because of the limited frame rate, if I'm moving the camera like that, I might miss some text because it might occur in the gaps between 2 frames. The most proficient users tested at multiple distances, in effect. Another thing is that the general concept of computer vision without sight, framing text, is very difficult. In many cases, the poor results that we get, both with SeeingAI and with our system, were because only half of the text was seen, like in the first video that I showed you. It is very difficult as a blind person from the output of the system to understand how you should move the camera. So this is an opportunity for better feedback. We have experience in a similar system in which we gave feedback to blind people on how to move the camera to better frame a document. And we're planning to export that type of interface for our system for seeing text. And I'm done here. I'll be happy to answer your questions.
Sorry, I missed you. Hello, my name is Kong Chen. I work for Argo AI, and my question is, have you think about generating a panoramic picture first and then do the OCR?
So the question was, why taking multiple pictures, doing OCR in each one of those, and why not doing it a panoramic? That's where we started from. I wanted to do a panorama. Panoramas condensed information, right? So instead of having multiple overlap pictures, they become one. So in a sense, they make for a faster processing. You just process one general image rather than multiple images. What we found is that even though automatic panorama generation is possible, and it still needs guidance on when to take pictures so that they overlap enough. When you do your stitching in a panorama, sometimes there are some tiny defects that occur. That's normal. That's well studied. If text happens to be there, OCR is not able to read it. So we had a number of false alarms in that situation, and that's why we decided to go for this lower system. I like the concept of redundancy a little bit because I don't know if it was visible in one of those examples, but for example, text was seen in one, was detected in one picture, but not in the other picture that still saw the text. That's because of different illumination conditions. But that's definitely a proper question, and I think eventually, ideally that would be the best, but it didn't work well for us.
Thanks for your speech. I have a question. In your experience, do you think that having, for instance, an RFID instead of having to scan a text is better or worse, or do you have experience about that? Thanks.
You're doing the exercise today. So having an RFID at the sign, or even a QR code perhaps, I would say a couple of things. First of all, RFID might not be the best example because you need to be pretty close to be able to read it, probably less than a meter. So we are back to square one. I don't know where the RFID is until I get there, right? That's the problem with RFID with blind people. The second issue I would say is that somebody needs to put it. So in the old times, back about 10 to 15 years ago, we thought that every single item in the market will have an RFID because we thought it would cost less than 1 cent. That didn't happen. So the whole work here starts from the assumption that there is not going to be any infrastructure change. The signs are already there. So certainly adding things like RFID or maybe an iBeacon or something else will simplify things, but that's an infrastructure change. It costs money. Somebody has to do it, and it's much less sustainable, in my opinion. Thanks, Steph.
Maybe one last question, and then.
Thank you for your talk. It was interesting to listen to. I was just wondering if there's any collaboration. Wait, do I have to use the mic? Yes. Oh, okay. I was wondering if there's any like collaboration between like the system when it tells the user when it vibrates that there is text in this picture. Does it at any point consult a language model to see like how likely is this text to be the complete image? You know, like that example that we saw where it was just seeing half the picture. Does at any point it consult a language model and say like maybe that's not the whole thing?
Yeah, that's a very good question. So would that be an interface to help you frame the system better? I would say probably not, maybe even at the text spotter level. The quick answer is that it does not have here, but that's exactly what I was talking about here. Let me just mention a quick thing. In our system, we developed 4 document reading. We had a system in which you would move the camera over the document, and the system would tell you, move up, move to the right, move left, really verbally. Because it was able to do some processing of the data to understand that if you move to the right, with good probability, you're going to get the whole frame. We didn't have it here. It is a little bit more complex here because the degrees of freedom are more. So you have 2-dimensional space more or less and 3 orientation. So you have to convey a little bit more information, but I think that's exactly where we are moving. Thanks.
Great. Last thing, Roberto again. Thanks. Thank you.